be ready to go. Let me hit you with these last two announcements. And fantastic, here comes the test and a paper. Excellent. Okay. This order. Okay. It's out of order here. The last two announcements are these. First, and I hope this doesn't pertain to any of you, but it could be pertaining to someone listening, or it could be someone you know needs to know this as well. Wednesday, day after tomorrow, the 30th of November, the last day to withdraw from a class, either for a full-term class or second mini-term class. So if you know of anyone who's struggling, who's in pretty bad shape, maybe someone you're tutoring, rather than getting a bad grade, consider withdrawing, because that's usually a better option than getting a bad grade. Okay. So anyway, last day for that is Wednesday, day after tomorrow. Secondly, they have now opened, or at least they told us they've opened the student course evaluations for fall term. So you know how to get to them? Yes? Okay. So go to your student course evaluations and do them for all your courses, especially now, and let me just say this. There's no way in the world I will ever know what you've marked, okay, at all. There's no way possible for any instructor to know if a student has made any mark at all, okay, what they've done. Now, I can tell whether you've done your evaluations or not, but I can't tell whether you, or what you said on the evaluation. So don't be worried that the instructor will know what you said. He or she or me won't, okay, we will not know, we cannot know. But we do see the composite scores, and those are important to us. So please, folks, do the student course evaluations. You've got until now, till the end of the term, and they usually even keep it open a few days after finals. But hey, I remember when I was a student, once that final exam was over with, I was out of there and wanting to get home to Christmas cooking and that kind of stuff, and forgot completely about doing course evaluations. So please don't put it off any beyond what you can. I'll be asking every day, have you done the student course evaluations? Please get those done. All right, that said, let me go on and mark the roll. I turned on that light before I'd done this, I don't know. All right, Ashley's not here yet. Tony is here. This light is right in my eyes. I can't line up. Okay, I think I got you. Cameron called in sick. Tariq is here. Victor's not here yet. Matt's here. Y'all are doing every other person, aren't you? Playing a game on me, okay? Javon actually did come in and turn in some work and have some questions, so I'll mark him, so he had to go back to work today. Jonathan's not here yet, and Nigel's here. So it's 1, 2, 3, 4 with one who came in earlier. Okay. Any questions on anything we've done up to now? Yes. When will I have it ready? Okay. I've looked at these dates, and I hope I've got them right now. As I said, Wednesday's the last day to withdraw. Okay? Then Thursday's the 1st of November. The following Thursday is the 8th of November. December. Okay. Thank you. I don't know what day it is, month it is, time it is. Okay. But the 8th of December, which is a week from Thursday, is the last day of class for full-term classes. If you're in a mini-term course, it goes on another day or two. But last day for full-term classes is Thursday the 8th. That's when I will pass out the final exams to you unless you need them earlier. Oh, wait, now this class meets Monday, Wednesday, so Wednesday the 7th will be the last day of this class. That's the last day that your paper's due, so get the papers in. And it's also when I'll be passing out the final exam, unless you need it sooner, and then I'll try to work on it sooner. Because I'm trying to anticipate how far we're going to get and know how far to go on the test. Okay? And it will be just on the last chapter we're working on. So we're in 14.3, and we'll only do a few more sections in this chapter, and then we'll move on to, I think it's 15, and try to get at least exposure to 15. Does that answer your question, kinda? Yeah. Okay, good. All right. All right, any other questions? Okay, what we're doing is continuing in chapter 14, and I think we finished 14.2, and we're ready for 14.3. And the title of this one is Partial Derivatives. That's what the first two sections of all the, getting a vision of what we're doing, or whatever they call that stuff, this is what we're leading to. Now, starting where they are indicating here, we have stressed that a function f, say, let me get my pen on black, f of two or more variables does not have a unique rate of change because each variable may affect f in a different way. Okay? We talked about that. For example, the current I in a circuit is a function of both the voltage and the resistance given by Ohm's law. So who cares about F there? That was just, oops. Okay. So what they said here is I, current, as a function of independently of voltage and resistance, okay, it's a function of both variables, and if you've had your physics, you probably know this is V over R, okay? Now, does I have a slope, a given slope? No. This is a thing, as voltage is going up, current is going up. But as resistance is going up, current is going down. So therefore, your current is following a path in the direction of voltage, it's increasing, in the direction of resistance, it's decreasing. Okay? So at any point, other than resistance equals zero, of course that can't happen. We're not counting superconductors. That's not going to happen. But anywhere along here, and by the way, we don't have any negatives either negative voltage or negative resistance, so we're not counting that. We're all in the first octant, you might say. If this is the V-axis and this is the R-axis, then anywhere here, if you're going increasing in V, you're going up, but increasing in R, you're going down. So who knows what your slope's going to be this way, and something in between, no matter where you are. So you can't say I has a slope at any one value for V and R. It depends on which way you're pointing. Okay? The partial derivatives are the rates of change with respect to each variable separately. Key word there, separately. A function f of xy, this is where I thought we were going to go before, of two variables has two partial derivatives. We have several ways for denoting those. One of these is f sub x, f sub y. Those are two partial derivatives of f, one in the x direction, one in the y direction. Okay? And how do we define these? Well, that's what this, goodness gracious, I'm about to sneeze. Sorry about this. It's going to wake everybody up. Sorry. Contagious, huh? Okay. Suddenly, I'm cold. I think my office is warmer than this classroom. So here's your partial of f, the partial derivative of f with respect to x at the point AB. Here's your definition, going back to limits. We'll find an easier way to do it, I promise you. But it's a limit as h is approaching 0, where h is the change in your x variable, the first variable. f of a plus hb minus f of ab. See, the only thing you're changing here is h in the direction of a. Okay? B stay the same. So these are your changes in your f, your function, per change in x. Because you're going from a plus x to a, from a to a plus x, so you've changed by x, h, not x. You've changed the amount of h. Okay, and the limit as this goes to 0 is your partial of f with respect to the x variable. Forget about the y variable with respect to the x variable at the point AB. F sub y at AB. Now we're going to forget about this x variable. It's not going to change. It's going to stay a. It is a. It doesn't change. It's the partial. And here's Jonathan, right? Yep. Can't see. All right. There we go. Partial of f with respect to y. And by the way, let me hit these two announcements again. Number one, the last day to withdraw from a class is Wednesday. So if you know of anyone, probably not you, but probably anyone else who may be in trouble, maybe someone you're tutoring and you don't see it, if there's any way they're going to pull that out, last day to withdraw is Wednesday, day after tomorrow. Last day of class is a week from Thursday, the 8th, which means your papers are due on the 8th. Now let's go back to the papers a minute, okay? Remember, you still can get a bonus point if you turn in the paper today, tomorrow, or Wednesday. That's the last day in November. After that, you turn it in December, you just get your score without the extra bonus point. Please get the papers in, okay? Now, second big announcement is the student course evaluations are now open. So anytime you get a chance, go out and do the student course evaluation. Okay. The partial of the function, the partial derivative of the function f with respect to the y variable, keep the x's the same. And that's a key. We're going to do it later, and do it pretty simply later, is the limit as k goes to 0. Just use another value here. K is an incremental change in the y variable because you're changing with respect to y. Of f of a, comma, b plus k minus f of a, comma, b. So basically over the amount k, the amount you changed in the y direction. So this is the change of the function with respect to, as y changes slightly, how does the function change? As y changes slightly, divided by the amount of change of y. As that amount goes to 0, that's your partial of your function with respect to the second variable, y. All right. Now, like I said, there are many notations here. Okay, just like there are many notations for derivatives. You can use the prime notation. You can use the Leibniz notation. Well, again, we got something that looks a lot like Leibniz, and in fact, they call it the Leibniz notation for partial derivatives. Like this. Partial of f with respect to x. That's the same thing that that's meaning. Okay? And notice the difference. A derivative is actually a d here and a d there. A partial is a crooked letter d. I mean, I don't know what else to call it. It's a symbol, but it's to remind you of d, but it's not really a delta, so don't get that confused. I don't know. It's just a crooked d. It looks like an upside down 9. You're absolutely right. A backward 6, okay, or something. Yeah, okay. Yeah, it's upside down 9 is probably better. That's the same as partial with respect to x. Partial of f with respect to y would be this. Now, when do you use this? You use the d if it's a single variable, independent variable. Use a partial if you have 2 or more independent variables. Partial of the function with respect to y. Okay? Now, we can do something else to it. Evaluate it at a point AB would then be this. Okay? Or partial of f with respect to y at the point AB. Okay? Now, how would you do that with the other notation? It's a little harder. You could do the same type of thing, but this is a little bit better notation to do that. Well, no, I mean, evaluate AB. That's the same as these. Now those are equivalent either way. Okay. Now, here is the key statement. Partial derivatives are computed just like the ordinary derivatives in one variable with this difference. To compute f sub x, or partial of alpha with respect to x, keep all the other variables. Now here we only have two, x and y. Hold y constant and just do the partial with respect to x. Okay? Treat y as if it's a constant. To do the partial of alpha with respect to y, treat x and any other independent variables as if they're constants, and just take the partial with respect to y. The derivative with respect to the one you're allowing to vary. I'm sorry, all that sneezing I was doing, and now here comes the flood. Sorry. I hate this. So let's sorry. Let's do example 1. Okay, I think what I'll do is clear. That's not what I want to do. Erase all the ink and just go from here. Compute the partial derivatives of f sub of xy equal f of xy. Now when they write that, that indicates x and y are both independent variables of x, of f. Independent variables of the function f. Okay? And when they say independent, they're independent of each other. One doesn't depend on one another. Therefore, you can hold one constant and take derivative with respect to the other. This function, in this case, is x squared y to the 5th. It says compute the partial derivatives of this. You tell me which partial you want to do first. X, okay? Partial of f with respect to x. And you can put it xy or leave that off. It doesn't matter. Since there's no value in there, you can just leave it off. What would that be? What do we say do? If you're taking the partial with respect to x, treat the y as if it's a constant. Okay? In other words, this would be cx squared. And what would be the derivative of cx squared? 2cx, right? Okay? So, but the c is just the y squared, so this would be 2x y to the 5th. You just treat the y as a constant, it just hangs in there, okay? Now, what's the other partial? You did the partial with respect to x, this would be the partial with respect to y. And what would that be? Okay, your x squared would be there. 5y to the 4th. Exactly. Okay? You just treat the x squared as if it's constant. Take the derivative of this, be 5y 4th. So it'd be 5x squared to the 4th. That's just part of the constant, as if that was a or b or c plus, whatever. Okay. Any questions on that?
Do they have the symbol in the book, or is that the way it's supposed to be on the Y part?
Okay. Okay. They wrote theirs this way. I guess I should have looked at the book. The partial of f with respect to x is that one, and partial of f with respect to y is that one.
Do you see on the line with the red block on it though?
Yeah.
D, whatever it is, y, and then they have x over here.
Oh, I see what you mean. Yeah, that is an incorrect. That should be a y there. I did not see that. Okay. Yeah, the second thing there, did extra steps in there, and in so doing create an error. That second one that says x squared partial with respect to y of y fifth. Yeah, that was a typo. Got it wrong. Okay, Victor's here. Good deal. And let me say again the two big announcements. Number one, and not saying this for your benefit as much as someone you may know, the last day to withdraw from a course is Wednesday, day after tomorrow. After that, you're going to get a letter grade. If you withdraw today, tomorrow, Wednesday, you get a W. W does not hurt you at all academically. May have some financial aid implications if you've withdrawn or passed or made a D, or failed or made a D in that course before. Then you won't be able to get financial aid for a third time. You can get it twice, but you can't get it 3 times. So that's the only negative implication I know of. It could delay your graduation, that kind of stuff too. But it doesn't hurt you academically. However, a bad grade does hurt you academically. So quite often it's better to do a withdrawal than the other. In fact, when I was at Georgia Tech as an undergraduate, it's a pretty tough school, okay? And the drop day was much earlier in the term. It was right at midterm, I think, or pretty close to that. And they had it on every calendar. In fact, the weekend after that, they had the Pink Parachute concert. That's usually the only concert we had all year, all term. They'd have a concert for drop day because a lot of people actually really did, by choosing to withdraw intelligently, they were able to stay in school. Otherwise, they could have easily got failed out. And back then, Vietnam was going on. You failed out, off to the races for you. Okay, so it was a different time and a different place. So believe me, schools were not begging you to come to their school. They had plenty of applicants. They were turning people away, and it didn't hurt them at all to flunk someone out because they had plenty more waiting to come. So there were no big scholarships, no big thing. Please come here. We'll do this for you. We'll do that for you. They said, make it or not. It's up to you. Never mind. We won't go back to that type of deal. All right. Let's look at a graphical representation of this. Okay. This is, blow this up. Don't think I'll get all 3 of them on at once, but I can get the bulk of 2 on at once. Okay. If this is your function, f is a function that picks some value a, some value b from x and y and gives it a value on the z-axis. So at any given point that's on this function, you see before in 2 space we got a curve, right? In 3 space you get a surface, okay? In 4 space you get a volume. We won't even go there. Okay, we can't picture anything beyond that anyway. But anyway, you get a surface here. Your A, your x value gives you your x coordinate there, B gives you your y coordinate, then you feed it into the function that gives you your z component. Okay? Coordinate. So this is your function at any point x, y. These are your values of z. It looks like a blue parachute here. Okay. Now, what a partial derivative is, you see, if you're at this point AB, f of AB, at this point right here, how can you talk about a slope? You can talk about a slope in the x direction, in the y direction, or in any other direction, and it could be going any which way you want. So since x and y are independent, we take the partials of each of those. And what the partial is with respect to x, that means we're going to hold b constant, okay? The y value is constant. So we're going to take this curve here, and this is your f of x curve when y is equal to b, okay? all along here would be your values. So the partial of f with respect to x, where y is constant at b, is the slope of this line right here. So you take that plane, slice it right through that, the plane parallel to the x-axis, the xz-axis, xz plane, and slice it through straight across the y-axis, perpendicular to the y-axis at point B. And this then is your derivative, the partial, the slope of your partial of f with respect to x at the point AB is the slope of that line right there. Okay? Just as if you had gone down to 2 space. Lose your y, focus on where y is equal to b, that plane where y is equal to b, this is your partial of f with respect to x, the slope of that line. The trace curve, you could call it, at x, b, f of x, b, okay? And any place here, the slope would be here, 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 whatever it would be on that curve. Okay, the partial of f with respect to y would then be the trace curve here. You say x equal a, that plane x equal a, slice it through there parallel to the plane yz plane, x equal b, x equal a, and then here's your curve, and the partial of, at that point, a, b, would be a downward slope there too. So this is a downward slope in x, so it's a negative slope in x, and a negative slope in y. But they don't have to. So it's like a much steeper downward slope here, a little bit shallower there. One could be going one direction, one another. That's what it means. Back here, x, y is equal to 0. It would be there. Y is equal to something else here, 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 here. So in that plane, x equal a, your trace curve. That would be the slope of that trace curve. Okay, does that make sense? All right, I think we're ready for example 2. I think this is the graph of it, which hopefully you'll never have to graph. Hopefully I'll never have to graph. Okay, but who knows? Calculate g sub x at 1, 3 and g sub y at 1, 3, where g of xy is equal to y squared, there it is, g of xy is equal to y squared over 1 plus x squared cubed. Okay. So it says calculate g sub x. Now, I think you know this, but I'm going to say it again. Be sure you do your derivative while you still got the variables in there, then plug in the point. Okay? Don't plug in the point and take a derivative. It's always going to be 0 then. So don't do that. Okay? Take the derivative of the function first and then plug in the values. Okay? So the first thing we're going to do for this one, it says calculate g sub x. So let's first do, and as soon as I do this, it's going to shrink, g sub x of xy. We'll go back and plug in 1, 3 in a minute. I think that's what, yeah. First, tell me what that is. Okay? Well, before you do that, I would rewrite this function. How would you rewrite it? You don't have to. I just was suggesting you do. I would rewrite it y squared, that was in the numerator, times 1 plus x squared, what? To the what? I can't hear you. Yeah. Well, I can't hear what you're answering. You may be saying it right. I just can't hear. Just to the negative 3. There's no square root sign in there. I know it shrinks it here. So this is y squared over 1 plus x squared cubed. Okay? So I would rewrite that in exponential notation rather than division. And I'd write this as that thing, 1 plus x squared to the minus 3. To me, that makes differentiation easier. You may not think so, but I think so. And I'm the only one that can't. No, I didn't say that, did I? Okay. So if that's your G, then what's your G sub X at XY? We'll start with XY. We'll go back and plug in. How would you do that? How would you do that? They promised rain today. I'm hoping we get it. All this wind, they better bring us some rain too. How would you do G sub X then? Hold Y as a constant, so that Y squared just like a constant, Y squared, okay? And what else would you do? Okay, I think I heard you say do a -3. You're counting the Y squared as if it's a constant, and then you do 1 plus X squared to the what? No, to the -4. Okay, now you got one other step to do here because of the good old chain rule, whatever you also got to do. Times derivative of the inside. So you did the derivative of the outside. Derivative of the inside is 2x. Okay, so then you'd need another 2x there. So I'm going to put the x in here and change the 3 to a 6. Are you okay with that? If I had planned ahead, I would have left more space there. But that's the 3 that you had there times the 2, that would be -6. So now rewriting that in a fractional type form, which is how they had it originally, would be -6xy squared over 1 plus x squared to the 4th. Okay? Now at this point, I plug in my 1, 3. They asked for it at the point 1, 3. So this would be G sub x at 1, 3 would be -6 times 1 times 3 cubed, right? Where did that cube come from? That's a square. Oh, I know. My pen drug. Okay. My pen is drugged. No. That's a 2. It just looked like a 3. All right. Sorry about that. If I don't pick up my pen, it drags, or if I don't pick it up far enough from the thing. Okay, so that'd be squared divided by 1 plus, well, 1 squared is still 1, but now that's to the 4th power, so this will be negative 9 times 6 is 54, 2 to the 4th power I think is 16, right? Right? Yep. And you can divide out a 2, and this will be -27/8. I'm hoping that's what it is there. Yeah, say I got a -27/8. Now what does that mean? Well, you find the place where x is equal to 1, y is equal to 3, and by the way, it looks like they're letting each space be 2. I mean, 2 spaces be 1. So there's 1, there'll be 1, 2, 3, and the curve here that has a negative, on increasing x as this is going down, so it has a negative value here. And they actually plugged in what that third value would be in here. That would be 3 3 squared is 9 over 1 plus 1 is 2, 2 cubed is 8, so it's 9/8. That's where that came from. And the partial of this with respect to x, okay, would then be the slope of this tangent line there, and that sure enough looks like it's a negative, a little bit more than -3 slope downward. Now that's pretty steep seeming, but that's what they indicated it is. Okay. Now, I think they also asked for the partial of g with respect to y, didn't they? Yeah, so let's do that one. Do it here. G sub y at xy. Always do it at the variables first and then plug in the numbers. All right. Now this one, folks, do you have to go back and write it in the other notation? Not really, because you see your x is, your denominator is all in terms of x. If you're taking the derivative of g with respect to y, this is just a constant. So whatever that is, just write it down, okay? And just take the derivative of this. What derivative of the numerator be? Yeah, it's the y squared. 2y, okay? Over the denominator. So the denominator is all x, there's no y down there. So that would be 2y over 1 plus x squared cubed. Okay? And then evaluating that at 1, 3 would be what? Say that again. Yeah, now at the second step you plug in 1 for x and 3 for y. So what do you get? Six over 8. Is that what you said? Yeah, 1 plus 1 squared is 1 plus 1 is 2. High level math today. 2 cubed is 8, and 6/8 is 3/4. Now that indicates you've got a positive slope this way. Now I don't know if they showed this. No, they didn't. I don't know why. But at the same point here, cut your line. They didn't do it. I'm going to try to do it. Though this is not going to be pretty, I promise. Well, they sort of have done it. Yeah, they have done it. I thought that was the x, y axis. Here's the thing. So the slope, this tangent line here, that the red tangent lines of this curve here, see that's just barely curving, and the tangent line here is just slightly positive. 3/4 is almost 1. Just appears to me they have this exaggerated on for the partial with respect to x, and probably under-exaggerated on the one with respect to y. That's the slope of that pink tangent line here, and this way is slightly positive 3/4. Okay.
Where did they get the 9/8 from? The z point?
The 9/8. Oh, yeah, okay. For any point on this curve, g, which is your z value, is y squared over 1 plus x squared cubed. So at the point 1, 3, that would be 1 down here, which is 1 plus 1 squared is 1. So that's 1 plus 1 is 2, cubed is 8, and then 3 squared is 9. So that's your z value at any point here. Okay? Just plug in what point you're at for x and y, calculate z, and that's where that comes. That's the function value. Then the derivative, or the partial, is the derivative value of that thing where either x is a constant 1 this way, or y is a constant 3 that way. Okay. that cuts that curve. That'll be the slope of that at that point. Okay, does that make sense? They are the slopes of the trace curves through 1, 3, 9/8. When 1 is held constant, that's your f sub y, and when 3 is held constant, that's the f sub x. Now, all right, Ashley's here. Okay. Let me also say this. Let me make 2 announcements I've made to everybody, so people listening at home are going to hear them a lot. Okay, listen up. The last day to withdraw from a class is Wednesday. I'm not suggesting any of you do so. You're all in pretty good shape, I think. But you may know of somebody, a friend, a classmate, someone you tutor, anybody that you know. If they're in serious problems in a course, you might want to consider withdrawing by Wednesday rather than taking a bad grade. Okay. Second thing is the student course evaluations are now open. So please do those sometime between now and the end of the term. I'll start asking you every time, have you done the student course evaluations? All right. This class is probably one of my best classes as far as getting papers in. I think I got my 5th paper in today, so only 4 of you have not turned in a paper. Please get those in. And as far as the first test goes, I have 4 of those in. Did I just get I just got one of those too.
That was
Test 2. Oh yeah, you had already turned in test 1. Okay, so test 1, I've still only got 4 in, so that means 5 of you haven't turned in test 1. And test 2, I've gotten the first one in, that means 8 of you haven't turned in test 2. So please get those done. We're running rapidly out of term. The other thing I announced before, in case I forgot to say it to the others that came in a little later, the last day to withdraw is this Wednesday, and the last day of class is a week from Thursday. So that's the 8th, last day of class. Well, in this class, it'll be Wednesday the 7th, okay, because we won't meet on Thursday. So on Wednesday the 7th, I will return all your other tests to you. So I do need those in by then, and I will also give you the final exam that day. We will have class that day, but I'll give you the final, and you can get it back to me anytime Thursday. You can give it to me, Thursday if you want to, Friday if you want to, Monday through Thursday of the next week. Now, technically, I would normally have said Monday through Friday of the next week, but I've got a meeting down in New Orleans it's on Friday evening, so we're going to have to leave Friday morning to get there. So I will be out of the office on Friday what is the date? 16th? Something like that. Whatever the Friday is, the end of the final exam, I will be out that day. So get me your finals by Thursday, okay? Your papers by the last day of class, remember. Get them to me today, tomorrow, or Wednesday, you get that bonus point. But anytime the next week or so, up until Thursday, last day of class, you just get your score. Anytime after that Thursday, during finals week, you start losing points off that. So please get them into it before the end of the term. Get me your test in and get I'll be returning those. If I get them all in, I'll return them sooner. But if I don't have them all in, by that last Thursday, I'll be returning all of those to you. Okay. Now, next thing they're discussing here, and it's worth a discussion. In fact, we already did it in example 2, okay? Now they tell us about it. We'd use the chain rule to compute partial derivatives of a composite functions, f of xy, which could be capital F of g of xy, where capital F of u is a function of one variable, and the u is a function of 2 variables. So here's basically what they're saying. The partial of f with respect to x if there's some, what they call it, intermediate function. That's a partial of capital F with respect to u times the derivative of u with respect to x. Because remember, u is a function. No, I'm sorry, I put the symbols in backwards. Okay. Sorry, the way they're writing it is this. Derivative of f with respect to u times the partial of u with respect to x. U is a function of x and y, but capital F is a function of u alone. Okay. Now, we've actually already done that, but the similarly partial of f with respect to y would be derivative of capital F with respect to u, because that's a function only of the 1, times the partial of u with respect to x. And that's what we did on the previous example 2. But now they're doing it again, so we'll do it again. So I think I will clear the screen. Okay, any questions? Okay. Compute the partial with respect to x of this function sine of x squared y fifth. They seem to like that combination. Okay. Now, how would you do this? And the order doesn't matter as much as just doing it. We're doing the partial with respect to x. How would you proceed? And there's more than one correct way, so tell me the way you would proceed. Help me. Second, keep the y constant, absolutely. Okay. If you're integrating, we usually substitute. Take the derivative, we just take it. Okay, what's the outer function here? The sine function. What's the derivative of the sine function? Cosine of the same thing. So that would be cosine of x squared y fifth. Now we take the derivative of the inner function, but with respect to x holding y constant, like you said, and what would that be? Second, 2x y to the fifth. You got it. Okay. Now you could have written that at the end, but it gets confusing there. You're wondering if you're taking the cosine of the whole thing. I like to write that in front. Okay, that's the way I did it. Now they didn't give it any particular value, so we'll just leave it like that. Okay. Now they go in and put the f of u is sine u, but u is a function of x and y squared, so, or x as and y's, and they go through the whole rigmarole, and we get the same answer. So I say, why do all that? Just do outer function, inner function. It usually will work out pretty well. Any questions on that? Say again? No, because you're only taking with respect to x. But you're absolutely right. You could have done the partial of that same function with respect to y. They didn't ask for it, but we'll do it. That's sine of x squared y fifth. And what would that be then? Okay, you still have the cosine of the same argument, x squared y fifth. 5 x squared y fourth. You got it. Now, later, not now, we can do second partials. And you can do mixed partials. And you can do same partials. So things really start getting a little more complicated than they were in the single variable case. But it's all doable. Yeah, but that's how you take it with respect to y. All right. What if we have more than two variables? Okay. I think we'll just clear these out. Any questions on this before I clear it? Okay. What we're asked to do is to calculate this value. F sub z of 0, 0, 1, 1. Now, obviously, how many variables do we have? Independent variables do we have? Four, because you got four numbers there inside the parentheses. And here's what your function is, where f of x, y, z, w. Strange thing they do in mathematics. They're so zoomed into x being the favorite variable, then if you got 2 dimensions, x, y, 3 dimension, x, y, z, 4 dimension, they don't go back and say w, x, y, z and put it in alphabetical order. They do x, y, z, w, okay, most of the time. It doesn't matter what you call them. You can name them in any variable in any order. You can make up names. Fred and Sue and Sally, I don't care. Okay, but here's your function. It's equal to e to the xy plus, no, xz plus y, I can't read. Oops. Yuck. Okay, there it is. Okay, let's get it back again. xz plus y over z squared plus w. Oh, and they did have to choose the z, didn't they? Okay. Now, you could take partial with respect to x, with respect to y, with respect to z, with respect to w. If you wanted to do that, you certainly can. But they're only asking for the partial of f with respect to z at those values. So let's just take the partial with respect to z. And what would that be? We'll do x, y, z, w now. And what would that be? What had you better do? What rule is this? This is a quotient rule. Now, how does that quotient rule go? Anyone remember? Oh boy. 125 review. Where's your tutor? No. There's a little sing-songy version, or just doing it straightforward. Which you like better? Either one. Okay. It's loady high. Start low and go, okay. Loady high. Loady high. What follows that? Yeah, but something in between. Minus. That's why the order matters. In your product rule, it doesn't matter which one you do. First under root of the second plus the second to the root of the first. You're adding, you're multiplying, there's no order. But when you're dealing with division and subtraction, order matters. That's why it's loady high minus ID low. Now here's how I remember that. Okay? Here's how I remember that. When you're taking derivatives of this, if you wrote this up here, it would have a negative exponent. So when you're taking the derivative of the denominator, it's going to be negative. So therefore it's low d high because that doesn't change the sign. Minus, because you're taking d low, that's going to give you a negative there. So it's minus high d low. Over what? No, over low or low squared. Yeah, low squared. Okay, no, just one or the other. Okay. So, tell me what to write. I gave you the sing-songy. Now you tell me what to write. Second? Okay. I think you said it. it's your low, which is z squared plus y times the derivative of the high, d high. And this is with respect to z. So that would be derivative of e is e, right? To the x z plus y, right? I did copy it down right, yeah. Okay. But now we have a chain rule, right? You're taking the derivative with respect to z. You did the e part, that stayed the same, but then derivative of the inner part is what with respect to z? Is it? Oh, the denominator's a w, isn't it? I don't know where I got that from. Someone watch out for me, okay? That's a w here and a w there. Sorry about that. Okay. I think I said w and wrote y. I don't know why. Okay. So that part's done. That's the low, and I started doing d high. I did the outer part, derivative of exponential, is the exponential, just like it's written. But now chain rule says you take the derivative of the inner part with respect to z. And what would that be? Second? Derivative of the inner part, that is the part up there, with respect to z. Yeah, derivative of this with respect to z. Remember, you treat all your other variables as constant. Say again? Okay, e to the xz plus y, that goes there. Derivative of this is itself. Then you do the derivative chain rule of just this part. And what's the derivative of that? With respect to the z. No? Okay, remember that's a constant. It would be the x. Derivative of a constant is 0. If the constant is multiplied by something, you keep it. But if it's added to something, no. Derivative of a constant is 0. So that would just be x. All right. Phew, goodness, that just fell away. I have to hold my thing in place. Okay. That's just the first part. Okay. All right. Now we have the minus. How does that go? Minus what? We did low d high minus high d low. Okay. Minus. Now what's your high? No, what? That's your e to the x z plus y, right? That's the high. What's the low? Derivative of the low part with respect to z. Say again? Okay. W is accounted as a constant. 2z times 2z. I'm going to put the 2z in front. Almost sounds like Uzi, but it's not. Okay. It's a minus 2z. I just don't like putting it afterwards. It gets confusing. Minus 2z e to the x. Okay. Over what? Z squared plus w squared. You got it. Yes. Okay. Now all we do is plug in the numbers. Okay. F sub z, but we evaluate it at 0 for x, 0 for y, 1 for z, and 1 for w. All for 1 and 1 for all. Okay. What does that give you in your numerator? What's your z? 1. So 1 squared is 1 plus w is 1. 1 plus 1 is 2. So there's a 2 out front. So I'm going to erase this parentheses because I don't think I'll need it. Okay. And then you have and x. But what's x? 0. That's going to make everything in that first part 0. So the 2, who cares? It's gone. Okay? Because the x is a 0. Okay? So we go to the minus part. Minus 2, and what's your z? 1, so that's minus 2, e to the 0 for the first one, plus 0, so it's e, what's e to the 0, by the way? 1, so that's minus 2 times 1. These 1s and 0s, they come in pretty handy, don't they? Okay, and what's your denominator? Okay, so that would be 4, and that comes out being a negative 1/2. So, f sub z, and they can't draw a picture of this one, by the way. This is 4 variables of 5th dimension. That's a singing group, by the way. But anyway, I can't draw it. So, but anyway, in that direction, the slope is negative 1/2. Let's see what, oh, look at that. They got it right, too. Good for them. Now, all right. All right, they go to something else now, and it's true. Because the partial derivative, f sub x, the partial derivative of f with respect to x, at some point a, b, is the derivative of this function, f of x comma b, okay? Because you're, it's a function of one variable along x, because your second variable is a constant, and it happens to be b there, okay? We can estimate the change delta f when x changes from a to a plus delta x as a single variable calculation, because it is. It's just a derivative. Similarly, we can estimate the change of y when y changes by amount delta y. So for these small delta x's delta y, and just how small depends on your accuracy required, you come up with, oh my, what was that a part of? That was, I didn't realize they had this. Go back to example 2. This is the second part of example 2. We've already done it. Sorry. What's that? Yeah, that was the g sub y. Yeah. And why they now are throwing it in there, I don't know. See, whoever did these slides, I mean, they randomly made slides and then they threw them wherever they wanted to. That was the second part of example 2. Okay? Here's where we are now. Okay? Up here, past example 4. Okay? Who put these together? I think they were throwing darts or something. All right. This is all that we were saying before. If you're estimating what the functional value is if you change the a, the first variable, by just a little amount and leave the second variable alone, then the difference here, this is your delta y, delta L, okay? Delta L here. And you're just changing a little bit on your x. Is approximately the first derivative, the partial with respect to x at AB multiplied by that change of x, delta x, okay? And you get that by the partial is this thing here divided by delta x, the limit, blah, blah, blah. So just forget about the limits as long as that delta x is small enough, multiply by the second delta x. And the change of F between a b plus delta y and a b, so you're only changing y by a small amount, delta y, then that would be your partial of F with respect to y, that gives you the slope, times the change of y, a little bit of change there, that would tell you how much the F's change. It's just the linear approximation of the change in those functions. Okay? This allows the function F in any number of variables for example, delta F would be F approximately equal to F sub W delta W. If one of the variables W is changed by delta W, all the other values remain fixed. Okay? Now here is an example kind of using that. Okay? Okay. Here's what we got then. This is a ball grid array, a BGA package, ball grid array. Multi-chip is a microchip, I can't read, microchip joined to a circuit board by a small solder balls of radius r millimeters, separated by a distance L millimeters, as shown in figure 3, this figure right here. Now the key here is the radius r here has to be a great deal less than the distance M. Okay? These radii here have to be a lot. And by the way, we want all these solder joints to be about the same. Average radius r, and that r has to be a good deal less than the distance between them. Okay? Now, sorry. It's a microchip joined to a circuit board, so the microchip is on top and the circuit board underneath, by this small solder balls of radius r millimeters, separated by a distance L millimeters. Manufacturers test the reliability of the BGAs, ball grid arrays, by subjecting them to repeated cycles in which the temperature is varied from 0 to 100 degrees over a 40-minute period. 0 degrees Celsius is what? 32 Fahrenheit, which is the freezing point of water. 100 degrees Celsius is the boiling point of water. So you're going from 32 to 212 or 0 to 100 Celsius from freezing point to boiling point of water over a 40-minute period. According to one model, the average number N of cycles before the chip fails is this. Of course, as soon as I write, it's going to shrink. N, the number of cycles before the chip fails, is equal to average number, good round number, 2200, where that comes from, just empirical, that's what they found, times that radius r, that's the radius of the solder balls, okay, divided by LD, where L is the length between the solder balls, and D is the distance. Well, they don't say what D is. Where D is the difference between the coefficients of expansion of the chip and the board. Okay? So, here we have the board here, and here we have the chip up here. There's some, as you heat and cool these things, there's shrinking or stretching. Stretching when you heat them, shrinking when you cool. But if there's some difference between the coefficients of linear expansion of those two boards, and by the way, this board looks a lot thicker, so even if they're the same material, this one's going to expand or contract more than this because this one has more volume to it. Okay, so anyway, there's a difference. D is the difference between their coefficients of expansion. Okay, estimate the change delta N. Oh, and by the way, I didn't finish this. This is raised to the 1.9 power. Not quite squared, but awfully close to it. Okay? Now, estimate the change, delta N. Okay? How much of a change this is the number of cycles before the chip fails. So what is that change of N? We use this approximation. Estimate the change delta N when R now is not a variable, it's a constant. R is equal to 0.12. They don't give any units here. Well, I think earlier they said they were millimeters. Okay. D is the change of linear coefficient of expansion, the difference in coefficient of expansion between the chip and the board, and they're saying that's 10. That seemed like an awfully big difference there, because I mean, coefficients of expansions are very small numbers anyway, so that's a little bizarre. And L is increase, so L is your variable here, and L is going from 0.4 to 0.42. So the change in your distance between the beads is from 0.4 to 0.42. So it's a pretty small change there. Radii are relatively small too. Okay. So we need to do that approximation. Well, what is that approximation? Delta N, according to what we just said, was the partial of N with respect to which variable is going to be changing? L, okay, times your delta L. Basically, that's what it's saying. Now look at that formula. And you tell me if that doesn't sort of suggest what we need to do. You're looking for a change of N, so that delta N, or they don't have a name for this, the partial of N goes on top here, so it corresponds here, for a change of L, because that's what's changing, times that change of L. Well, this almost looks like these cancel out, giving you delta N. So you see the formula sort of suggests to you what you're trying to get. And this will be approximate. It's not exact, but it'll be approximate. Okay? So we really need approximate equal to here. So the first thing we've got to do is take the partial of N with respect to L. And where does the L show up? In the denominator, right? Okay? So therefore, that's really all we're kind of interested in. That's going to be, I think I would rewrite this as, now this may not turn out being a smart move, but I think I would rewrite it as 2200 R L to the minus 1, D to the minus 1, and that's raised to the 1.9. I don't know if that's going to be helpful or not. In fact, don't worry with D. D's a constant here, so just put that over D. Forget about the D to the minus 1. Okay? Okay. But I think that'll give it to us. Now we want to take derivative of that, the partial of that with respect to L. All right. Where do we begin? Okay. The trouble is you raise the whole quantity to the power of 1.9. So I think there's several ways to do it, but I think I might also do this. 2200 R over D to the 1.9 times L to the minus 1. Well, let's just write that as L to the minus 1.9. Okay? Do you buy that? And is this what you meant by separating it out? Okay. Then I agree with you. I didn't know what you meant at first, but yeah. Then I agree with you 100%. Okay? Now, all we've done is rewrite the equation here. We haven't taken the partial yet. Now take the partial, and what would that be? Okay, negative 1.9 L to the minus 2.9, I agree with that, times this whole thing, 2200 R over D to the 1.9. Okay, that was all a constant. It stays a constant. I think I probably would have written it in front, maybe after the negative 1.9, you know, between that. But yeah, that's what you've got. Now let's plug in. Okay, now there it is. Here's what our approximation is. So let's evaluate this at these values here. R equals 0.12, D equals 10, and we do L equals 0.4. That's our initial L. The delta L is 0.02. So we'll deal with that in a minute. So let's plug in those numbers down here. All right. And I'm tempted to do the 22, and that is an R there, my pen drug again, over D. So 2200 times 0.12 divided by 10. In fact, let's just do this. Let's just wipe out 1 0, and that'll wipe out the 10. So 220 times 1.2, get what that is, raise that to the 1.9 power, and tell me what that number is. 220 times 0.12 raised to the 1.9 power. You got it? I'm sorry. Yeah, that's right. Okay. Multiply that by a negative 1.9 times 0.4 raised to the negative 2.9 power. Okay, I think we're ready to go then. If you've got that calculated. Anyone do that? Or I'm just here talking to myself. Okay, someone was punching along, weren't they? Do I need to say it again? I wish I had a calculator that would work. You want me to run down to my office and get one? Okay. All right. Okay. What do you mean total? Then are you multiplying it by delta L, which is 0.02, or before you do that? Okay. Okay, wait. The 0.04 is no, there's no 0.04, it's a 0.02. It's changing from 0.4 to 0.42, right? So that's the change of L is 0.02. Did you use that? Or 0.04? Okay, divide by 2 and you got it. Divide that answer by 2 and you got it. It did. When it saw the posse coming, it cleared out. Okay. Okay. Shall I go get my calculator? Okay. Y'all just wanting to get me out of the classroom, aren't you? Okay. Someone got it? I'll be right back.
Still got one trying to use this math way out to do my calculations.
That's what I use now too. Yeah. Is your calculator radio mode or degree mode? I just changed to degree mode, that's why I had it really.
You did. All right. You just want to get me out of the classroom. Okay.
I had the radio mode.
It shouldn't matter. You're not taking a sine or a cosine or anything, but okay. So what we did here is the partial of this with respect to that would be this thing to that power. So that would be, there it is up there. It's 220 because we divided out the 10 from here. Okay, 220 times R, which is 0.12, raised to the 1.9 power, multiply by that by negative 1.9 times L, which is 0.4 to the negative 2.9, and that gave you what? And then did you multiply that by 0.02? And what? A little louder.
Negative 272.18.
0.18. Okay, I think we can probably drop that. Well, let's see what they do. Yeah, they did about minus 272 cycles. Well, remember what the N was? Is how many of those changes from freezing to boiling, freezing to boiling, freezing to boiling, 40-minute intervals, how many times it took before the chip failed, okay? And they said 272. Now, the question, which I think would be a legitimate one, is what do we mean by negative in that case? That would be how many cycles it took before it failed, okay? I don't know why it comes up negative. That doesn't seem to make physical sense.
What was the negative 13,000 represented?
Okay, negative 13,000. Where did that come from?
13,609. Before we multiplied that by 0.02, what was that?
Oh, that was, okay. That was this thing right here. The partial of N with respect to L, okay? How many temperature changes did it take, cycles of changes, did it take per delta L for every incremental change that you have here, okay? And that came up a negative number, which as you're suggesting, still makes you wonder, why is that a negative number? I don't know. They tend to just lose the minus sign and go with it, and just say, well, they keep the minus sign. The decrease in the average number of cycles before a chip fails is that.
They worded it differently, decrease.
Yeah, that's how they did it, but what do they mean by decreasing the number of cycles? Manufacturers test the reliability of VGAs by subtracting the repeated cycles of these temperature varied from that to that over a 40-minute period. According to one model, the average number of cycles before the chip fails is this. Estimate the change. Okay, got it. What happens if you change this from 0.4 to 0.42? I mean, just move them a little bit further apart, see what happens. The number of cycles before it changes actually decreases by this. That's what this means, by about 272 cycles before you have a failure. So by spreading out the L there, you drop the number of changes before you have a failure. That's not a good thing, so probably better to have them closer together than further apart. Okay, that's right. That's what it's regard to. All right, now, in the next example, we estimate the partial derivatives numerically. Then f of x, f sub x, and f sub y are limits of the difference quotients. We have the following approximation when h and k are small. And this is what we're leading to here. Okay, now we're doing it the other way. Okay? We're estimating the partial derivatives numerically if we know the rest of the story. Okay? So, if we know what the change of f is for a change of y, then that's approximately what your partial derivative is. Okay? As long as that delta y is small enough. Okay? And similar approximations are valid in any number of variables. Okay? That's easy enough said. Here's example 6. Okay? Now, I don't know if you've run into a graph like this before, but they're a lot more common than you may think. For instance, are any of you planning to become mechanical engineers? No? Oh, possibly. Okay. Okay, another. I think mechanical engineers are typically the ones that design cooling systems or delivery systems of any nature. You know, something's coming out. Maybe it's water out of a pipe or air out of a duct or whatever. Well, the size of your duct, the number of angles in your duct, you can have a bunch of different variables, and they'll have these curves, and you're representing actually 3 independent variables here on a 2-dimensional graph, which is a pretty decent thing to do. Here we have change of temperature this way, change of salinity this way, and change of, I think it's density that way. This is a contour map of seawater density as a function of temperature and salinity. So basically what they're asking you to do, and this is, compared to what we have been doing, it's really pretty straightforward and simple. Seawater density, rho, kilograms per cubic meter, depends on salinity, capital S, that's your horizontal value here, parts per thousand, and the temperature in degrees Celsius. Use the contour map of seawater density appearing in this figure to estimate d rho dt. Okay, we're looking now, and there's the figure. You're going to have to look at it more carefully now. Okay, I think I already had that. Okay, we're estimating d rho dt. Partial of rho with respect to temperature. Okay? At the point A. Okay? Here's the point A. And we're looking for change of rho, which would be for change of temperature. Well, the change of rho is either this way or that way. Your temperature is changing here, so you're changing, what is that, 2 degrees Celsius. Pretty interesting number they chose there. That's what global warming is. They're trying to hold it to 2 degrees Celsius change, so that's sort of interesting. They're not talking about that now. But what is the rho dt as A is changed, and you're going with respect to T, so you're going from A to B. Well, what would that be? That would be the change of rho over the change of temperature. Well, what is your change of rho? Going from one level curve to the next. What is the change there? Minus 0.0005. Right? You go from this curve to that curve. Minus 0.0005. Yes. Is it time? Okay, this will be pretty quick. Negative 0.0005 over 2 degrees. So what would that be? Yeah, and the units are bizarre. Kilogram per meter cubed per degree Celsius. Okay? Yeah. All right. And then the second of those is the estimate the change of density per change of salinity. So how we're going, change of salinity is going from there to there, one density change. So that is now a positive 0.0005 divided by change of salinity. That's 33 to 33.7. So that's a 0.7. And someone plug that in on your calculator and see what you get. This is partial of rho with respect to S. And they estimate it to be 0.000. Just plug it in, you know, it's pretty simple. And that would be kilogram per meter cubed per PPT, part per thousand. Okay. Strange units, but done. All right. All right. You occasionally will see those graphs, and somewhere here, once upon a time, I had a pencil. There it is. We'll begin next time by higher order partial derivatives. Homework exercises you can do here. We came close to finishing, not quite. Any of the odds 1 through 7. Any of the odds either 9 or 11 or both. Any of the odds 13 through 39, I think you can do those. Any of the odds either 41 or 43 or both. 45. 40, any of the odds 45 through maybe 55, 45 through 55. We'll pick up the rest of those next time. Good deal. Catch you on Wednesday. All right, good deal. Thanks. All right, we'll end this one.